Hey guys, today's video we're going to look at two sample inference procedures with means, and we're specifically going to look at independent samples today. So grab some paper and let's get started. When we're looking at two sample procedures with means for inference, today we're going to look at both confidence intervals and hypothesis test for two independent samples. When doing this, the goal of these inference procedures is to allow us to compare two treatments, so we can compare the response or the outcome from two different independent treatments, or we can compare the characteristics of two different populations. Let's say we're looking at college males and college females and their study habits, or maybe we're looking at college males and college females and something else. So we can compare those two different populations. In doing so, we have two independent samples from each treatment or from each population. So our goal here, what we're interested in comparing today, are the difference in the means between the two treatments or the difference in the means between the two samples. In order to do this, we've got to remember a few calculations that we've done earlier this year. So we need to know how to find the mean of the difference in two random variables as well as the standard deviation of the difference for two random variables. So let's review those real quick. Remember, when we're finding the mean of x minus y, it's simply the mean of x minus the mean of y. So the mean of the difference between two random variables is the difference in the means of those two random variables. But when we're dealing with standard deviation, our variability or our standard deviation never cancels. So even though we're finding the standard deviation of the difference in x and y, remember, we're always adding the square root of the sum of the variances of those standard deviations. Or in other words, the standard deviation of x minus y is the square root of the sum of the variance of x plus the variance of y. When we're doing the difference of means today, we're going to be using this to find the standard error in our calculations. All right, so we're going to go back through. We're going to take a look at an example. We're going to be able to describe a distribution. We're going to look at the normal curves. We're going to calculate the probability of a difference in random variables. We're going to look at a sampling distribution, and then we'll go ahead and look at confidence intervals and hypothesis test for two sample means today. Let's say we have a population of adult men, and they have a mean height of 71 inches and a standard deviation of 2.6 inches. And let's say we also have a population of adult women with a mean height of 65 inches and a standard deviation of 2.3 inches. I'm telling you here to assume that the heights are normally distributed. So let's go ahead and describe the distribution of the difference in heights between male and female adults. So remember, when we say that we're going to describe the difference, we're talking about cuss and BS. So we're going to talk about the center, the shape, the spread, anything unusual, and then we need to make sure that we're describing the distribution in context. So if both of my populations, my heights of men and my heights of women, are normal, then the difference in their heights will also be normally distributed. So we know that we're going to have a normal distribution, and we need to calculate the mean and the standard deviation for that normal distribution. We're going to do that with the two calculations we just reviewed. So we would say the distribution of the difference in heights between males and females is normally distributed with a mean of 6 inches and a standard deviation of 3.471 inches. We have nothing unusual because we have a normal distribution. Let's take a look at a picture of these normal distributions. If we draw these female and male curves on the same scale, we see that our female normal distribution is centered at a mean of 65, and our male distribution that's normal is centered at a mean of 71. If we calculate the difference of those two distributions, males minus females, we get a new curve centered at a mean of 6 inches with a standard deviation of 3.471. Notice my difference curve, or my difference distribution, has a greater standard deviation than the male and female curves. Remember, on that calculation, when we're combining random variables, our standard deviation is never reduced. We're always adding the variance of each of those random variables and taking the square root. We're not canceling any of the standard deviation. So if you notice, our difference in male and female curve also normally distributed, but its standard deviation is going to be larger than the standard deviations that we calculated or that we were given for males and females. Now that we've got this difference male minus female curve, we can use this to answer questions about probabilities on this normal distribution. For example, what is the probability that the height of a randomly selected man is at most 5 inches taller than the height of a randomly selected woman? So what we're looking at here is the difference in heights between males and females. So we're going to take a look at that curve. Remember, this curve was centered at a mean of 6. This curve was our difference in heights, and we calculated that by taking males minus females or men minus women. So I want to know what is the probability that a randomly selected man, their height, so X, we'll call this X man, is at most 5 inches taller than a randomly selected woman. So that's the height of the man minus the height of the woman or the female. That difference is at most less than or equal to 5 inches. So we're really calculating the probability on this difference curve of getting a difference less than or equal to 5. So on your calculator, remember, you're going to calculate a normal CDF. My lower bound on this is going to be negative infinity. My upper bound is going to be the upper bound of the shaded region of 5. My mean is 6. This curve is centered at a mean difference of 6. And my standard deviation is 3.471. This gives me a probability of a difference in height being no more than 5 of 0.3866, or we have a 38.66% chance that a randomly selected man and a randomly selected woman will have a height of at most 5 inches of difference, where the man is taller than the woman. Let's take a look now at a percentile calculation for the same distribution. What is the 70th percentile for the difference male minus female in heights of a randomly selected man and woman? Remember, we're still dealing with the same normal curve here. This is a normal curve with a mean of 6 and a standard deviation of 3.471. Because I'm asking about male minus female differences, that's the normal curve that I'm going to use. If we're calculating a 70th percentile, that is actually asking me what value are 70% of all of my values at or below. So the area below this point is going to be 70%. Now, sigma is known here. We're using a normal curve, so I'm going to find the value on the curve when this represents the man minus female, height of a man minus the height of a female. To do this, we know that we have a normal distribution. We know the area on our normal distribution, so we're going to calculate an inverse normal. So this is where we're going to calculate the area below that point, which is 0.7 for my 70th percentile, a mean of 6, and a standard deviation of 3.471. This gives me the point on my curve. If it would a standard normal curve, it would be a z calculation. Because I have a curve centered at 6 with this standard deviation for the difference in heights, this represents the difference of heights to be 7.82 inches. Now, in these two examples, we were looking at the difference in height between one man and one woman. Let's take a look at a sampling distribution, where we're looking at a difference of sample means. In a sampling distribution, we're not looking at individual heights, we're looking at sample means. So now the question changes. What is the probability that the mean height of 30 men is at most 5 inches taller than the mean height of 30 women? We need to go back and take a look at our calculations on our AP Stats formula chart, page 5, for looking at the mean and the standard deviation for a two-sample mean. When we do that, we will see, if we're dealing with a normal curve here, right, we're talking about the probability that my X bar for men minus my X bar for females, my mean difference in heights. So I'm really not looking at individual values now. We're saying we took a random sample of 30 men and a random sample of 30 women, and we're finding the difference in the means from those random samples. So we're looking for the mean of the men minus females for the random sample of size 30. That's still going to give us our same center on our curve of 6 that we've been dealing with. But now we're looking for the standard deviation for X bar men minus X bar women. So this is a standard deviation of sample means. On your formula chart on page 5, you see the calculation is the standard deviation for the first population squared, or the variance, divided by the sample size, plus the variance for the second population divided by that sample size. So remember, anytime we're dealing with a sampling distribution, we've always got to take into account our sample size, and we always take that into account. Well, here our sample sizes are the same. So we would simply say that we're looking at the standard deviation squared for the first population over the sample size of 30, the standard deviation squared for the second population over the sample size of 30. We can do a little bit of math here. Remember, if we're adding or subtracting fractions that have the same denominator, we keep the denominator and add or subtract the numerators. And when we calculate this, we get a standard deviation for the sampling distribution for sample means of 0.633772. Now we're going to use that in our calculation. So now let's draw this curve again. We've now got a normal curve centered at a mean of 6. And our standard deviation for sampling distributions of sample sizes of 30 is 0.633772. So now our probability calculation, we want to find the probability that the mean height of 30 men is at most 5 inches taller than the mean height of 30 women. In other words, our mean height of men minus our mean height of women, sample size of 30, that mean height is at most less than or equal to 5. So remember, this curve is now our sampling distribution of mean height differences. So each of these is a male minus female mean height. So we're taking a look now at this normal curve. We're going to go normal CDF. We're looking for at most 5. So our lower bound is still negative infinity. Our upper bound is still the upper bound of our shaded region. Our mean is still 6, but now our standard deviation has changed because we're dealing with a sampling distribution of sample means. So when we calculate this answer, we get 0.0573, or we have a 5.73% chance of getting a difference in heights of at most 5 inches. Now let's take a look at that second calculation, but dealing with sample means, or sampling distribution of 30 men and 30 women. Again, we're asking for the 70th percentile, so we want to know at what value 70% of all of my values fall at or below. But now we're looking at the difference for the mean heights of men minus the mean heights of females or women. So now we're looking for the inverse normal. And again, we're going to ask area below, which is our 70th percentile, the mean, and then we're using our standard deviation for our sampling distribution of sample means for sample size of 30 men and 30 women. When we calculate this, we get the 70th percentile to be 6.332 inches. That means the difference in a random sample of 30 men and 30 women, 70% of all of those samples will have a difference in height of no more than 6.332 inches. All right, so we've kind of reviewed sampling distributions and probability calculations. You now know how to find your mean and your standard deviation for a difference of two independent samples. Let's take a look at inference. We're going to go back and do the same question we asked at the beginning. When we're dealing with two sample procedures with means, when we're dealing with inference, our goal is to compare the response to two independent different treatments or to compare the characteristics of two independent populations. Okay, in order to do that, today we're going to look at independent samples from each treatment, or if we're looking at two different populations, we're going to look at independent samples from two different populations. So the rest of this lesson, we're going to take a look at our confidence intervals and our calculations and our hypothesis tests. We're going to look at inference. Remember, anytime we're doing an inference procedure, it always starts with assumptions. So we need to review our assumptions now that we have two samples that are independent and we're looking at means. So let's take a look at the assumptions we're going to do for a two-sample test for means. The first assumption is always whether or not we have a random sample or randomly assigned treatments. Now that we have two, we're going to say that we have two simple random samples from our populations, or we have 2 randomly assigned treatment groups. Then we also are saying today we're only looking at independent treatments or independent populations. So our second assumption that we have to check is that both of our samples are independent of one another. We always have to talk about normality. We're assuming that both distributions, not just one, are approximately normal. Well, how do we do that? Well, both distributions have to have a large enough sample size, or both of our graphs have to show that we have an approximately normal distribution. So we're either going to have to check that both samples have large enough sample sizes for our central limit theorem, so at least 30, or that both graphs of our sets of data, we're going to have to graph both. Either we look at 2 normal probability plots and they're both linear or approximately linear to give us an approximately normal distribution, or we're going to look at 2 box plots and look at the box plots and verify that there are no outliers and both distributions are approximately symmetric. And then, of course, our last assumption when dealing with t-inference is sigma. So we have to look at whether sigma is known or sigma is unknown for both of our samples. Now, realistically, in real life, we are not going to know both of our population standard deviations when we're doing inference. So today we're looking at t procedures. So we're going to look at 2 sample t confidence intervals and 2 sample t hypothesis tests. Remember that our t procedures and our t critical values and our test statistics are all based on degrees of freedom. Our degrees of freedom are sample size -1. So what do we do when we have 2 different samples? How do we calculate the degrees of freedom for the problem? Well, to do that, we actually have 2 options when calculating degrees of freedom for 2 sample inference. The first, option 1, is that we use the smaller of our degrees of freedom, either a sample size 1 minus 1 or the sample size 2 minus 1. In looking at the smaller of the 2 values for our degrees of freedom, this is going to produce conservative results for us, higher p-values and lower confidence. So that is certainly an option. Option 2 is that we are going to use a calculation to approximate the degrees of freedom for our 2 sample t procedures. The calculation looks like this. And don't worry, we're not going to memorize this calculation. This is an approximation used by technology, which means your calculator is going to do this automatically. Since our calculator does this, this is going to give us a better approximation of our degrees of freedom. It won't give us as conservative a value as option 1. So option 1 can often give us high p-values and lower confidence. Since we have calculators throughout our exams, we are going to use option 2. We're going to have our calculator calculate degrees of freedom for us automatically. All right, let's review confidence intervals. Remember, when we're calculating a confidence interval, it's always our statistic plus or minus our critical value times the standard deviation of our statistic. Today, we're looking at our statistic at being the difference in our sample means. So our statistic is going to be our sample mean 1 minus our sample mean 2. We're looking at the difference between 2 independent sample means. Our critical value is going to be our t critical value, because we said realistically we're not going to know both population standard deviations. And then our standard deviation of our statistic is going to be the square root of our standard deviation for our sample 1 squared divided by n1 plus the standard deviation for sample 2 squared divided by n2. Remember, this is an approximation of the population standard deviation of our statistic. We're using sample data to approximate population data, so this is really called the standard error. It's the best thing that we've got to use when we're calculating our confidence interval. Now, in doing 2 sample procedures, you're going to be asked whether you use pooled procedure or not. When we're talking about a pooled procedure, we use this when we have 2 populations with the same variance. When we pool, we're averaging the 2 sample variances to estimate a common population variance. We are not going to use pooled procedures on the AP exam. The reason is we really don't know the variances of the population, so we're going to not use pooling. Your calculator will say pooled or not pooled. You're going to select no. We're going to tell the calculator no for pooling. All right, so we're going to go through a complete example of a confidence interval, and then we're going to look at a hypothesis test after this. So let's get started. We have 2 competing headache remedies. They both claim to give fast-acting relief. We're going to perform an experiment to compare the mean length of time required for bodily absorption of both brands, brand A and brand B. Assume the absorption time is normally distributed for two brands. 12 people were randomly selected and given an oral dosage of brand A. Another 12 were randomly selected and given an equal dosage of brand B. The length of time in minutes for the drugs to reach a specified level in the blood, whatever that level is for bodily absorption that shows that the remedy is working, was decided. And the following were the results. Brand A, you can see the mean standard deviation and sample size for that sample. Brand B, you get the mean standard deviation and sample size for that sample. So first, let's describe the shape and the standard error for the sampling distribution of differences in the mean speeds of absorption. Well, we said brand A and brand B bodily absorption was both normally distributed, so we're going to say that we have a normal distribution here. When we have a normal distribution, we talk about the mean and the standard deviation. So our mean, so this is going to be brand A, so the mean of A minus the mean of B. So this was just 20.1 minus 18.9. So this normal distribution with a mean of 1.2. And then our standard error, remember that calculation is the square root of our standard deviation for sample 1 squared divided by N1 plus our standard deviation for sample 2 squared divided by N2. So if we calculate this, we get brand A 8.7 squared with a sample size of 12, brand B with 7.5 squared with a sample size of 12. We get a calculated standard error of 3.316. So when we describe the distribution, we talk about the shape, the center, the spread, and since it's normal, there are no unusual calculations to take a look at. All right, now let's find a 95% confidence interval for the difference in mean lengths of time required for bodily absorption of each brand. So we're going to look at the difference in brands A and brands B, or our sample mean for brand A and our sample mean for brand B. So we're going to do a complete confidence interval calculation starting with assumptions. Our first assumption is that we have two independent randomly assigned treatments. We also were given that the absorption rates were normally distributed and both of our sigmas are unknown. Now, I actually combined the first two assumptions that we have, or two of the assumptions. We have a simple random sample and our samples are independent in this first statement. We have two independently randomly assigned treatments, so we've taken care of that. Assumptions have been checked. Now let's do our calculations. Our formula and our calculations for a confidence interval for a difference in two sample means is mean 1. So this is our sample mean for brand A minus our sample mean for brand B plus or minus our t critical value times the standard deviation of our statistic. Obviously, you can do this in your calculator as well. Remember, when you're calculating a confidence interval, you either have to name the confidence interval by name or formula. So you could include this formula that I'm drawing right here. You would get credit for naming it by formula, or by name, it's a two-sample t confidence interval for means. The correct confidence interval calculated goes for a difference in absorption times of negative 5.685 up to 8.085. Now we can have a negative here because of the order of subtraction. So if we have a negative, that means brand B actually worked faster than brand A. If we have a positive, then brand A worked faster than brand B. Now, if you notice on this calculation, we used a t critical value. We need to be able to calculate that t critical value. So we could do a couple of different things here. On your calculator, if you do a confidence interval, your calculator will give you degrees of freedom, which is 21.53. So 21.53 is the calculator approximation for degrees of freedom. If we're looking at that calculator approximation, think Price is Right. Like what's the closest without going over? That's approximately the same as degrees of freedom of 21. So if I were going to calculate my T critical value, looking at a 95% confidence interval, that means 0.025 above and 0.025 below. So I could calculate my T critical value. I could look at the area below. I could go inverse T, and the area below is 0.975, and I could use my conservative estimate for degrees of freedom, and I would get a T critical value of approximately 2.080. So that's really where this comes from. We can calculate this on our calculator, and then we can figure out the T critical value that was used to calculate this. Let's take a look now at our conclusion in context. Our conclusion would state, we are 95% confident that the true difference in mean lengths of time required for bodily absorption of each brand is between negative 5.685 and 8.085. Notice here, remember, our conclusion has to talk about the fact that we're really inferencing or predicting what the true population difference in mean lengths of time is. So this is where you're going to say the true difference or the population difference or the actual difference, and we're looking at difference in mean lengths of time required for bodily absorption. So when we take a look at this calculation right here, we're looking at the difference in the length of time, the mean length of time for brand A and brand B. Now, I highlighted this because there's actually two different confidence interval statements we could look at, whether we're dealing with inference that's independent samples or matched pairs. Today we're looking at inference that's independent, so we're looking at the difference in means. We're going to look next class at dependent or matched pairs inference. So let me show you what that would look like if we were dealing with a matched pairs here. In dealing with a matched pairs, you would refer to the mean difference. We'll look at that next class. But today we're dealing with two sample inference, so we're referring to the difference in the means, mean length of time A and mean length of time B. All right, now let's look at doing a hypothesis test. First, we need to look at our hypothesis statements. Remember, our null hypothesis is always that there is nothing going on here. So if we're comparing the difference of two population means, our null hypothesis could easily be that mean 1 is equal to mean 2. Or in other words, the difference in mean 1 minus mean 2 is equal to 0. We can actually write this either way. So we could look at the difference in means to be 0, or we could rewrite this as mean 1 is equal to mean 2. So there's no difference in the population means. Status quo, nothing going on, nothing to look at. We could write this either way for our null hypothesis. Now, in looking at our alternative hypothesis, it could be that the difference in the means is less than 0. It's a negative difference if we took mean 1 minus mean 2. Doing a little bit of algebra, that also means that mean 1 is less than mean 2. We could also have an alternative hypothesis where the difference in means is greater than 0, or that means that mean 1 is greater than mean 2. And then finally, we might not know which one is greater, but we know that they are simply not equal to 0. Their differences are not 0, which means the two means are not equal to each other. Now, in dealing with our hypotheses, you've now used two different variables here, mu1 and mu2. Remember that you have to define both mu1 and mu2 in context so we know what you're referring to when you write your hypothesis statements. In dealing with a hypothesis test, we always have to calculate a test statistic. So in calculating our test statistic, it's always our statistic minus the parameter divided by the standard deviation of our statistic. We're dealing with T inference, so we're going to do a T test. Our statistic is going to be the difference in the means, the sample means, sample mean 1 minus sample mean 2. Our parameter is the difference in population means divided by the standard deviation of our statistic. Now, the hypotheses we just wrote, our null hypothesis said that the mean 1 minus mean 2, the population mean 1 minus the population mean 2, this right here in our null hypothesis was 0. If we're dealing with a hypothesis where this equals 0, we can actually leave this out because it's a difference of 0. And so we could actually simplify this calculation and leave that out. So let's take a look back at the original example where we're comparing the length of time in minutes for drug A and drug B to reach a specified level in the body. Here are the results from that test. We're now going to calculate a hypothesis test. Is there sufficient evidence that these drugs differ in the speed at which they enter the bloodstream? To do a hypothesis test, we always start with our assumptions. Remember, we check these assumptions for confidence intervals. We have 2 independent, randomly assigned treatments. We were given that the absorption rate is normally distributed in the stem of the original question, and both of our sigmas are unknown. Now we need to write our hypotheses and define our variables. The null hypothesis is going to be that mean A, brand A, and the true mean of brand B are equal. There's no difference in the drugs. And then we want to know, is there a difference? We didn't specify which works better, so mean A is not equal to mean B. Mu A is not equal to mu B. And then, of course, we have to define these parameters. Mu A is the true mean absorption time for brand A, and mu B is the true mean absorption time for brand B. We now need to calculate our formula and our calculations for our t-test statistic. Our t-test statistic is the sample means. Remember, our null hypothesis here is there's no difference, so our population means our parameter would be 0, divided by the standard deviation of our statistic. We get a t-test statistic of 0.361. This means if we're looking at our calculation here, we get a t-test statistic of 0.361. Our p-value is the probability of getting this test statistic or one higher. In other words, getting these results or something more extreme if indeed the null is true and there is no difference in the mean absorption rates between the 2 brands. Our degrees of freedom are calculated with our calculator, and we're going to use an alpha or a level of significance of 5% to perform this hypothesis test. Remember, our p-value was finding the area of one part of our curve, and we're doubling it. This is a 2-tailed test. So we're actually calculating a 2-tailed test statistic here. If we get a p-value of 0.721, what is going to be our conclusion? In this case, we would say since our p-value is greater than alpha, we would fail to reject the null. There is not enough evidence to suggest that these drugs differ in the speed at which they entered the bloodstream. All right, so let's take a look and break this down for a second. Anytime we're looking at a hypothesis test, we always have to say what we do in terms of the null hypothesis. So in this case, we would fail to reject the null, and we have to give a reason why, linkage. So our p-value is greater than alpha. That's part of our conclusion. We really believed that the alternative was true. That's why we carry out a hypothesis test. Remember, the power of our test is to correctly identify an alternative hypothesis that's true. So we also have to write our statement in terms of the alternative hypothesis in context. There is not enough evidence to suggest that these drugs differ at the speed with which they enter the bloodstream. If we think about our calculations for our confidence interval that we calculated for this question earlier, we got a confidence interval that was a difference between negative 5.685 and 8.085. If you look at our difference, mean A minus mu B is equal to 0, that's our null hypothesis. Since the null hypothesis is contained in our confidence interval, from our confidence interval we would also fail to reject the null. We are 95% confident that the true answer lies, the true difference and the absorption rates lie somewhere in this interval. If 0 is in the interval, then we don't have any evidence to reject the null hypothesis. What if our calculations in this test had given us a sample mean of brand B, an X bar for brand B of 16.5? Then could we conclude that brand B is faster? So in other words, what I'm really asking you to do here is go back and do this hypothesis test again, but using a sample mean for brand B of 16.5 instead of our original answer. So the difference here is a little bit larger. This gives us a new test statistic, a new p-value, same degrees of freedom in alpha, and the question is now can we prove that brand B is faster, that there's a difference in the brands? In this case, our p-value is 0.2896. It's still higher than alpha. We would still fail to reject the null hypothesis. When doing calculations for hypothesis test, we've talked about robustness. If we're talking about being robust, a 2-sample procedure is more robust than a 1-sample procedure. Ideally, we would like to have equal sample sizes if possible, especially if we're setting up a test. We would like to get an equal number of participants taking brand A of a drug and an equal number of participants taking brand B of a drug, but it is not required, although it is ideal. All right, we have one more hypothesis test to do real quick. This one's a little bit different. I'm changing the null hypothesis now, and so we're going to look at what happens when our null is not a difference of 0. So let's take a look at one last hypothesis test before we go. A modification has been made to the process for finding a certain type of time 0 film that begins to develop as soon as the picture is taken. Because the modification involves extra cost, it will be incorporated only if sample data indicate that the modification decreases the true average development time by more than 1 second. Should the company incorporate the modification? So this is our difference. We are looking now at a null where we're trying to prove that something is more than a difference of 1. So on the last example, our null difference was 0, and our alternative was either greater than 0, less than 0, not equal to 0. Now our null and our alternative are going to be based on a difference of 1, but this actually changes our test statistic calculation. So in order to do this, we have the original data, 1, 2, 3, 4, 5, 6, 7, 8. We have a sample size of 8, and we have a sample size of 8 for our modified, time 0 film. We need to go through and we need to calculate our original and modified mean and standard deviation so we can do this hypothesis test. So we need to know the sample mean for the original data. We'll call this 1, I guess, and this is 2. Sample mean for 1. We need to calculate the sample mean for the modified. We need the sample standard deviation for the original and the sample standard deviation for the modified. So take a minute to calculate all of those. You can put this in list and spreadsheets and do one variable stats, and then come back to me so we can finish this example. All right, step 1 in a hypothesis test is our assumptions. We are going to assume that we have 2 independent simple random samples of film. Both distributions are approximately normal due to approximately symmetric box plots or the approximately linear normal probability plots. And so we can take a look at all of those. Those would be our approximately symmetric box plots for our original and our modified film. We could also look at our approximately linear normal probability plots. There are some deviations from linearity here, a little bit of a deviation from being normal, but remember our 2-sample procedures are more robust. So we are going to continue with this test and assume normality. And then both of our population standard deviations, our sigmas, are unknown. Now we need to write our hypotheses. Remember, we're testing here whether or not there is a difference in the original and the modified film developing time, and that difference, in order for us to produce the modified film, because it's more expensive, had to be more than 1 second. So that's really the alternative that we're trying to prove. Our null hypothesis is going to be the difference is equal to 1. So remember, not that there is no difference now, but that the difference is 1. And our alternative is that it's greater than 1. So that would be the difference in our true population means. And then, of course, we have to define our variables. For mu, we're looking at the true mean developing time for the original, mu O, and mu M is the true mean developing time for the modified. Or mean 1 and mean 2, you could call them that as well. So our t-test statistic is our statistic minus the parameter divided by the standard deviation of our statistic. We're going to show both our calculation and our formula. Make sure you're showing the formula so that we can tell that you're using a 2-sample t-test for means. Notice now that we have an actual parameter difference of 1, not a parameter difference of 0, because our null hypothesis has changed here. We get this calculation to be a t-test statistic of 0. We are looking at a p-value of 0.5, degrees of freedom of 7, and level of significance alpha is 0.05. So our p-value here is greater than alpha. So we would say, since our p-value is greater than alpha, we fail to reject the null. There would not be enough evidence to suggest the company should incorporate the modification. All right, there you go. We've looked at 2 sample means. So we've looked at 2 sample confidence intervals, t intervals for means, 2 sample t-tests for means. In both cases, our samples are independent. If you have any questions on this video, jot down those questions, bring them to class next time. We'll start by answering any questions you have. Bye-bye.